Thank you very much. First, thanks to the organizers for inviting me to give these lectures, and thanks to all of you for coming. So I'm going to give some idea on how to construct a theory of the glass transition, a simple one, not complete, but I mean I will try to give some idea on how to start. And okay. The talk will be, I mean, the lectures will be at the blackboard. I have some material, some kind of lecture notes that are extracted from a book we are writing. I have to figure out how to give them to you. I'm not sure I can give you all the book because it's not yet published, but I can probably extract some part and circulate it. But okay, they said you can interrupt me when you want, if you have questions. And I'm going to stay all the week and also on Saturday. I don't know exactly when are the, I mean, there are tutorials and in any case, on Saturday I will be free. I will be here. So if you want to ask me questions, I'm around. Okay, so now let's start. I think you had an introduction to the basics of the glass transition. And I'm going to consider a system of n particles. Also, tell me if I'm writing too small or if I should go more. I mean, I'll try to move in this direction up to, I don't know, there, but I mean, if you don't see, let me know. So n particles in a volume V. And, okay, density will be n over V. And temperature T, and there will be some pair potential V of R. And, okay, and of course I will consider the thermodynamic limit, where N and V go to infinity with constant rho and T. So, okay, rho and T will be the control parameters. Now, so this will be the system. Okay. And I will consider identical particles. So, all the particles will be identical and the pair potential will be the same for all pairs. And I think you have been told that if you do that, you don't get the glass, it will crystallize. And that's true. But still, I will insist on monodisperse for 3 reasons. The first one is that it's simple. It will simplify all the calculations. And since I'm going to talk about the mean field approach, in this mean field, I will use MF for mean field. Okay. So in mean field, I think I'm writing smaller now. So in mean field, it doesn't make a big difference. And so essentially, the phase diagram will be the same. Okay. It will be a... Let me know. But I can write bigger, so let me know. Just interrupt. Okay. So all the results will be essentially independent on the polydispersity, and you can generalize the calculation to polydisperse systems, just heavier. Yes, that's the next item. So 2. If you raise the dimension, that's what I'm going to do, and I will explain it in a second why. So if you consider D bigger than 4, then essentially also monodispersed particles do not crystallize. Okay, so in 3D and in 2D they will crystallize, but above 4 it becomes harder and harder to crystallize, which is also an interesting problem. So I think Patrick Charbonneau is going to talk about it, but if not, we can discuss this in some tutorial or some. Okay, and the third reason is that in the theory, even if your system is crystallizing in a simulation or in an experiment, in the theory, you can always select the liquid. So the liquid is a metastable phase. The crystal will be the stable phase. But in the theory, you can always choose to remove the crystal and focus on the metastable liquid phase. And I will explain how to do it. But essentially, so in theory, you can select the liquid by imposing translational invariance, essentially. You impose that your system is translational invariant, so it cannot crystallize. So, okay, that's the reason, and okay, it's just a matter of not adding indices of particle species. If you want to consider a binary mixture, you can do it. You just have to add a few more indices. Okay, so I will consider monodisperse systems of this type, and the last thing is that I will consider the limit where the dimension goes to infinity, dimension of space. So you can, okay, you are of course interested in 2D or 3D, but it's very convenient to consider d equal 4, 6, and eventually infinite, because this will simplify a lot all the description and essentially coincides with the mean field limit. So the advantage of, okay, first of all, okay, you might be interested in the mean field theory. I mean, this is what you do every time in statistical mechanics where you want to study a new problem, you start by doing mean field. And okay, sending the dimension to infinity is one possible way of doing mean field. There are many other ways, but for some reason, this is the one that is the simpler one in glasses. And so if you do this, you have two things. The first one is that you can really have an exact solution in this limit. So you can solve the thermodynamics, the dynamics, and I will also introduce some kind of modified thermodynamics to describe the glass. And you can solve it exactly for the potential that you want, essentially, in infinite dimensions. So this means that your theory will be exact for a given microscopic model that is well defined. It's a bit strange. I mean, you are taking a strange limit, but at least it's a well-defined microscopic model. So your theory will be free from pathologies if you want. So I mean, the problem is that if you want to stay in 3D, and you say, okay, let's try to stay in 3D and do some approximation. You can do that. For example, when you do mode coupling theory, that's what you do. And it works very well. But then every time you consider a new physical situation, you have to check that the approximations that you made are correct. And for example, when you do mode coupling, there are many situations in which it works very well, but there are also a few situations where you have problems, and then it becomes a bit hard to understand what's going on and why your theory is not working, okay? So if you do this, you have the advantage, okay, you are taking a very abstract limit, and the theory will be quite far from 3D, but at least you say, okay, you are sure that you can take your theory, you close your eyes, you do calculations, and it will give you the exact solution for that model. So it's not, I mean, it will always have a meaning. Then you have to, of course, you have to compare if what you're getting in infinite dimension is close to what you have in 3D or not, and it's not always the case. So this is one motivation. And the other thing is that, okay, you can hope then to make to make some kind of systematic expansion around the infinite dimensional limit. So let's say in 1 over d. So you can try to do this analytically, or you can do simulations. So in simulations, you can do, okay, you can try to do simulations as a function of dimension. And Patrick, I think, will show something. Essentially, you can reach dimension 12, and you can see how things change from the physical dimensions you are interested in up to the mean field limit. So this gives you an idea of the quality of what you're doing. And I think Patrick will discuss this. So I will not try to convince you that this theory is a good starting point for a theory of the glass. I will just So the aim of these lectures will be to describe what happens in this limit. And then I think Patrick will try to explain what works and what does not work with this approach. Okay, now, let's start with the simplest problem, the simplest problem, which is computing thermodynamics, thermodynamic quantities. And then I will move to dynamics today, and I will probably not finish the dynamics today. And then tomorrow I will continue with the dynamics. And once we are done with the dynamics, I will try to show you how you can reproduce the long time limit of the dynamics via a modified thermodynamics calculation. And then I don't know exactly, depending on time, I will try to show some applications. So, okay, the thermodynamic in infinite dimension can be constructed easily using the virial series. And I think you should know the virial series. Do you? Okay. If you don't, I mean, I will explain what it is, but I will not derive it. If you want that someone derives it, let me know. I mean, I will not do it today because it's a bit of time, but we can organize to have a derivation. Anyway, so the virial series is very simple. I mean, the idea is that you can construct a free energy that depends on the local density. Okay, so rho of x is going to be the density of particles around point x. And you can write this, and F is going to be the free energy. So you fix a density profile in your system, and then you want to know the associated free energy, and you can write this as a term which is the ideal gas. And then you have corrections around the ideal gas that come from the interaction. Okay, so this would be the very dilute limit. And then you add terms. So, okay, now I hope I have all the expression correct, but I mean, maybe the sign is not correct, but anyway, this is just to give you the structure. So you have integrals. For example, you have a two-particle interaction with a function f. So the function f is called the Mayer function, and is the exponential of minus beta v minus 1. Okay? So the Mayer function, if you have a potential that is repulsive when the particles are close, so if you plot it as a function of distance, when particles are close, the potential is going to be infinite if you have repulsion. So this term is going to be 0, and so it goes to minus 1. And then at large distances, when particles are supposed not to interact, the potential is going to 0, and this function is going to 0. So it's going to be something like this if you have only repulsion. And if you have attraction, at some point the potential becomes negative, so you have something like this. Okay? So the first correction is something like this, is an integral. So this is essentially telling you that this is the energy, if you want, or something related to the energy. It's not exactly the energy, because here you don't have V, but anyway, it's a correction that tells you that you have some density in X, some density in Y, and then you have to integrate over all space on X and Y and with this factor. And this will give you the two-particle term. And then you have other terms that I'm not going to write, but you can draw diagrams like this, and so on. And the first, this triangle, so each diagram represents a factor of rho on each vertex, a factor of f on each link, and then you have to integrate. So for example, this triangle is going to be an integral over x, y, z of rho x, y rho z, and then you have f of x minus y, f of x minus z, f of y minus z. And then you you keep write in terms like this. And you have a series of diagrams that you can characterize. Okay. And in principle, if you are able to compute all the diagrams, then you have the free energy for any density profile. So this is the virial expansion. Perhaps you have seen it in the form of pressure, but pressure is the derivative of the free energy, so it's a similar expansion. Now, why the infinite dimensional limit simplifies things? It's very simple. If you look here, what you can show, and this is a series of work by Riviere, Frisch, maybe with a C, Riviere, Frisch, Klein, Weiler, and Perkus, starting from I think around 84, and there is a series of papers going up to 1999, where they studied this series in the limit of large dimensions. And essentially what happens is that you can stop here when you are in infinite dimensions. And the reason is that if you look to this diagram, this is exponentially smaller when D is large than this one. And this one is going to be exponentially smaller than this one. And this one is going to be exponentially smaller than this one, and so on. Okay, then you say, okay, fine, diagram by diagram, it's fine, but you have an infinite number of diagrams. So can you resum? Can you show that really the series is well behaved in infinite dimension? And okay, this is more difficult. It's essentially still open. So in the last paper of 1999, what they did was to, okay, at each order, so if you look to the diagrams with 3 vertices, you have a triangle. With 4 vertices, you have a square, and you can add links. And then at order 5, you have a pentagon, and you can add links to the pentagon, and so on. So the state of the art, if you want, is that you can show that at each order in density. So, for example, if you look to the ones with 4 densities, this one, this is easy to show. This one is exponentially big than the others, so you can drop the others. And so at each order, you can keep only the ring. So you keep the triangle, the square, the pentagon, the hexagon, and so on. And you can resum all of them. But you're still throwing away many diagrams. But if you resum all these diagrams, then you get an expression that is easy to study. And you can look to this paper of Frisch and Perkus, 99, where they do this, and they show that the sum of all these diagrams is still essentially dominated by this one. Okay, then it could happen that all these diagrams create a problem, but there are also numerical studies of the diagrams, and it really seems to work. So I will assume it works. Exponentially smaller than. Mm-hmm. The problem is that, okay, in some regime of density, even if each diagram is individually small, the series is dominated by very large orders. So you have a problem of interchange between the density, the order of the series going to infinity, and the dimension goes to infinity. And so it's a bit tricky. But you can show that it's still fine. So I can give you. Yes, essentially this is exponential. You get something like exponential of minus d times a function of n, where n is the order of the ring. And for large n, this function can be arbitrarily close to 0. So you have, even if each order is fine, there are large rings that can be dominant. So you have to resum the rings. But once you resum them, you realize that it's fine. And then still you have the problem of the non-rings, and this is open. It's not really under control. But okay, there are simulations that more or less support that this is fine. So, okay, I don't want to enter into a long discussion of this, and essentially what I'm going to do is, okay, drop everything and say, okay, this is my free energy in infinite dimensions. Yes. Sorry. Sorry, I didn't understand.
Is there an intuitive argument to say why we...
Is there
an intuitive?
Intuitive. Yes. Yes, there is an intuitive reason. And the reason is that, okay, if you want, so this first term is describing interactions between pairs of particles. So you have a particle that is touching another particle. Touching, I mean, I'm thinking now that these particles are, for example, hard spheres or something quite similar to hard spheres. So this function f goes quickly to 0 when the distance is large. So in order for this term to have a contribution, the particles should be close. Now the next term, which is the triangle, it means that you have 3 particles and they should all touch to give you a contribution. So this is exponentially smaller than just the contribution of 2, which essentially means that the probability that you have 3 particles that touch all together in infinite dimension is very small. So essentially, if 2 particles are neighbors, and this particle has another neighbor, the probability that these 2 are also neighbors is very small. Because you see, in 2D, okay, it's easy to form triangles. In 3D, it's a little bit more difficult because you have more space. In large D, it becomes increasingly difficult. And okay, one way to think this is that the Kisin number, which is the number of particles that you can put around a sphere in D dimension, grows exponentially with D. So in principle, if you are in large dimension, you have a sphere, you can accommodate an exponential number of spheres around it. But if you look in a liquid how many neighbors you have order D neighbors, so much smaller than exponential of D. So essentially you have a particle that is surrounded by D neighbors, but there is space for exponential of D particles. So these D neighbors are going to be very far away from each other. And that's why you don't have... Okay. Thanks for that. Yes, I'm coming to that. Yes, you have to impose a little condition on the potential. So actually, the papers that I just erased, these were all done for hard spheres. So just pure hard sphere potential. But you can generalize the discussion to slightly different potentials. So, okay, that's the next point I wanted to discuss. For general potentials, I mean, in principle you can, because you can start adding diagrams. But okay, it becomes very quickly very hard. Okay. Yeah, I mean, it's... Okay, no, I agree. It's not very convenient to make a 1/d expansion on this. Okay, now, what kind of potentials I can use? So, okay, sorry, just one last thing. So I will say, okay, my liquid in infinite dimensions is described by this free energy functional that I cut at this point. And now, if I want, what I was saying before, okay, two more things. The first is that then you can also compute the G of R. So the G of R, which is essentially the probability of finding 2 particles at distance R, is going to be e to the minus beta v times a series. So there is a series of diagrams, but I mean, you can, throwing away all the diagrams here corresponds to stopping here at the first order. So in infinite dimensions, G of R is going to be an exponential of minus beta v of R. And now, the last thing is that now, as I said, you can, in the theory, you can select the liquid. So here it's very easy. You just say, okay, the liquid is characterized by homogeneous density, right? The liquid state is homogeneous. So I have to, I mean, unless I put some external potential, but so I just take a constant, and this will be, so the free energy calculated on constant rho is going to describe the liquid phase. So even if the liquid phase is metastable with respect to some crystal, so the crystal would have some periodically modulated rho. So this can exist in principle, but I can kill this solution by imposing just that rho is a constant. So in the theory, I can do that. And I can do that also if I add more diagrams, of course. It's not restricted to this. No, this is already the average. Rho of x is already the average density profile. I mean, you should imagine that you have a point, you take a small volume, and you take the average density around that point. It's not the sum of delta, it's the average. It's the thermodynamic average. When you construct the virial series, Okay, so now we have the free energy of the liquid. So, okay, which kind of potentials we can use? Okay, this is shared by the two sides. So, potentials. So the problem is that, okay, look, for example, to the second virial. So the coefficient B2, which is derived from this by taking uniform density, you put it here and you simplify some factors. And then you get the second virial coefficient, which is the integral. So I will suppose that all the interactions are spherically rotational invariant. So everything is just a function of the distance. So if I put this into the second virial, I get this expression, which is essentially this. Once you put rho equal constant, you put it out. One of these two integrals becomes a volume. You simplify the volumes. So you get integral over x of f of x. And then you use the rotational invariance. So omega d is the solid angle. It would be 4 pi in 3 dimensions. It has some expression that we don't need to specify. And then you have a radial integral of this form. Now, when you do this integral, what you see is that, okay, let's do this drawing better. What you see is that the Mayer function is doing something like this. So this is f of r. And then you have this factor r to the d minus 1, but this is growing exponentially. Okay? So you have to, so in this integral you have a kind of competition between this term that is growing exponentially, so it wants to get contributions from large distances, and this term, which is the Mayer function, that is cutting large distances. So you find a full analysis of the problem in a paper by Jorge and Thibault Membour, so it's Kurchan. It's on Archive 2016. So in this paper you find all the analysis, I mean a detailed analysis of the competition between these two terms, but I will just consider a simple class. And okay, the idea is that if you want something that is non-trivial, because you see that, I mean, if the integral is dominated by points in this region, then there is essentially no interaction. If it's dominated here, there is too much interaction. So what you want to have is something that is dominated by this range. Let's call it L. Usually it's called sigma, but I mean, it's the effective diameter of the particles, okay? So I want the integral to be dominated by what happens around this scale. So what I'm going to do, I will try to make it such that R is L, which is a constant, times 1 plus h over d, where h is a variable. So I will try to change variable. So h is going to be d times R minus L over L. And I will assume that the potential V of R has the form of some function V bar of this variable h. Okay, I will give you examples. So, okay, one example, it's hard spheres. So for hard spheres, the bar of H would be infinity if H is negative, and 0 if H is positive, right? Another example would be soft spheres. So this is, so if I take V of R of the form of L over R to the power 4D. So why 4D? Because in D equal 3, this is going to be 12. I think you are used to this. It's the potential 1 over R to the 12. It's the repulsive part of Lennard-Jones. It's a potential that is used often in numerical simulations of glasses. So, but I have to put a D here, because otherwise the integral will never converge in large D. If I use the potential 1 over R to the 12, and I send the dimension to infinity, then this factor is always going to win. So I need, in dimension D, in order to have a finite second virial, and in order to have a finite thermodynamics, I need the potential that goes at least as 1 over R to the D plus something. So I will choose 4D. So if I take this potential and I express it in terms of the variable H, you see that this is equal to, I put, instead of R here, I put L times 1 plus H to the D, so I get 1 over 1 plus H to the D to the power 4D. And when D goes to infinity, this becomes exponential of minus 4H. Okay? So this will be my function D bar of H. Is this clear? This is the exponential. But these are examples, but you can construct many other examples. So there are many potentials that are well studied in 3D that you can generalize to any D, and you can put in this form. For example, sticky colloids, or WCA potential, or Lennard-Jones, or essentially all the potentials that we use in glasses can be put in this form if you scale properly the exponents in the. So if you have these kind of potentials, then you can write B2. So B2 will become, you have minus omega D over 2, and then you change variable to H, okay? So you have, this is going to be, okay, when R is going to infinity, H is also going to infinity. When R is equal to 0, when R is equal to 0, H is minus D. Then you have DH, and okay, dr is equal to dH times L over D. Then you have R to the D minus 1. So this will bring a factor of L to the D minus 1. So this becomes L to the D. And here you get 1 plus H over D to the power D minus 1. And then you have exponential of minus beta V bar of H minus 1. Sorry for the confusion on the blackboard. Okay, so, and here I just changed V of R into V bar of H. And then I take the limit of infinite dimension, so I get, here I get this factor here, I will call it phi bar over 2. So phi bar is equal to L to the D times omega D over D. And this is, yes? No. Okay, let me, I finish this and I answer to your question. So this will be, okay, the integral will go from minus infinity to infinity dh. This becomes the exponential of h, and I'm done. So now, okay, what am I doing? I'm just trying to impose a form of the potential that is such that this second virial is well defined. I mean, is well defined. I mean, it becomes something, some finite integral over h times a prefactor, which is some Okay, this will be related to the packing fraction, just in 1 second. How do I do this? I impose that V of R can be written as a function that is finite. So V of R depends on D in general. For example, because there is this exponent that depends on D. It has to depend on D because if I take 1 over R to the 12 and D is 100, everything is divergent. So my potential depends on D, but I want to write it in a way that is a finite function that does not depend on D, okay? But the dependence on D is only through this argument. So H depends on D. And it's a change of variable. Okay? So then the only thing I did here is to make this change of variable. And I mean, because the potential depends on D only through H, once I change variable to H, the dependence on D in the potential disappears. And then I get a dependence on D here, but I can take the limit of D infinite, and this becomes an exponential of H. Did I answer to your question? No. Okay. But, okay, this is going to be important, so if it's not clear. Okay, sorry, and essentially, so the last thing I want to say is essentially what I'm imposing is that this function f of r is going from 1 to 0 in a narrow interval of order 1 over d around the typical scale. I mean, then L can be taken to be 1, it's a unit of length. But essentially what I have to impose is that this function f becomes quite steep. So you could think, okay, but then you're essentially always doing Earth spheres. But no, I mean, if you can do calculation for this potential, and it's different from Earth spheres. Okay, even if it looks like this, it's getting very steep, but in infinite dimension, everything is getting very steep around. Okay. Yes, this is the Earth sphere potential. And because H goes from, in infinite dimension cases, H goes from minus infinity to infinity. And positive H means that the particles are outside their core, and negative H means that the particle. Exactly. Exactly. Okay. Okay, you can consider more general functions f, but okay, for this you can check the paper of Jorge. I will stay within this class of potentials. Okay, so now we are done, because I mean, yes? Is what? 1 over d, yes, is the, essentially, you see R is L, which is the reference length, times 1 plus h over d. So when h moves of order 1, R is moving by order 1 over d. Yes, yes, when dimension increases, the function will be more steep. You can do the exercise on new plot. You can take this function, you choose R to be 1, and you will see that plotted as a function of R, it will essentially become a hardcore potential, hard sphere potential. But plotted as a function of H, it becomes an exponential. And you see that then the second, but the point is that there is this factor of R to the D that is compensating. So in the end, the second virial will be some function of V bar. And if you put here the hard sphere potential, you get something. If you put this potential, you get something else. So, I mean, in this limit, it looks like all the potentials are becoming hard sphere potentials, but it's not true. You can obtain different thermodynamics if you choose this one. Okay? Okay, so now we have the thermodynamics, okay? Because I told you that the free energy is cut at the second virial. I computed the second virial. This is my expression of the second virial, so I have the... sorry, and I wanted to say, okay, this thing, what is this thing? So this is omega d over d is the volume of a sphere. Omega d is the surface of a sphere of unit radius, is the solid angle. Omega d divided by d is the volume of the sphere of unit unit radius. So if I multiply by L to the D, this is the volume of a sphere of radius L. Okay. I'm going to clean up the blackboard, but just, so this object, sorry, there is a factor of rho that I missed everywhere, right? But, no, okay, sorry. Okay, okay. Actually, what matters is not B2, but is rho B2, right? In the pressure, you have rho B2, so let's put the rho everywhere, just to get, and then I define, okay, then I get rho. So you see that this object phi bar is the density times the volume of a sphere of radius L. But actually, if I want to define a packing fraction, L is the diameter of my particles, so I need to, so this is going to be 2 to the D times the packing fraction. Because I would like to have the volume of a sphere of size L over 2, of radius L over 2, which is the, so I have to scale by 2 to the D. Anyway, this is not really important, but okay. So okay, now we have the thermodynamics, and we can, so the pressure is going to be 1 plus rho B2, or something like that. So once I have B2, I have all the, no, because, no, that's true, but this factor, I'm assuming that the potential V is going to 0 sufficiently fast. So it's true that this is correct only if H is of order 1, but this factor is going to kill the integral for large H. So when, okay, okay, this, for hard spheres, this function is 0 for H positive, and it's and it is -1 for H negative. So for H negative, this is -1, and this, okay, this term is exponential of H, and so even this integral is cut off by -d, but the exponential of H goes to 0 very fast, right? When H is negative. So I don't need the tail. It's not going to be dominated by the tail. I mean, you can check, okay, let's do it. If I take hard spheres, so for hard spheres, from this expression, what I get is B2 equal to minus phi over 2, and then I have to integrate between minus H and 0, e to the H, and this term is 0 for positive H, I don't have contribution, and for negative H, this is -1, so sorry, so I get plus. So this is this integral is 1, so this is phi over 2. Okay, and you can check that this is the correct second virial of hard spheres in any dimensions. So the integral is dominated by small h. Okay, so with the thermodynamics, rho B2. Sorry, rho B2, yes. So, and the pressure is 1, the reduced pressure, beta P over rho, is 1 plus rho B2. So it's going to be 1 plus this phi bar over 2 for hard spheres. And for generic potential is going to have, there will be a factor here, some function I of beta, which is this function here. Okay, so I hope I convinced you that we can have the thermodynamics of the liquid. So all that we did here was for the liquid. There might be crystals in ID. That's actually a very important open problem in mathematics, to study the crystals in ID, but we kill them by imposing that the density is uniform. Okay, now I would like to start the discussion of the dynamics. So I will erase the blackboard, and while I erase the blackboard, you can think if you have questions on this. what is the I of beta is this this factor. So for hard spheres, it's 1. And for example, for this potential, it's going to be some function of beta. It depends only on beta because the density is only here. Okay. Now, dynamics. So for the dynamics, there are two possibilities. One is the, let's say, exact way of doing it, which would be to introduce okay, I'm going to study the Langevin dynamics, and the way to do it would be to introduce a path integral representation of the Langevin dynamics, and then this will have an associated free energy, and the free energy has the same form of the thermodynamic one, and then you do something similar. But it becomes very technical very quickly. So I'm not going to do that because it's impossible in lectures. So I'm going to do I'm going to follow a very different path, which will be to give some hand-waving arguments that, however, bring to the good result. So I will show you the hand-waving arguments, and at the end I can comment on how one could derive the same exactly, I mean, via the exact solution. So the setting is going to be the same, and V of R is going to be scaled in the way I was mentioning before. But for the moment, we don't need this. So, okay, I will consider equilibrium dynamics. Of the liquid. And I want to study what happens when I approach the glass transition and how it becomes slow. So equilibrium dynamics means that I start at t equals 0, I start with probability that is exponential of minus beta h over z. And then I run dynamics. So the dynamical equation is going to be something of this form. I have some inertia. So xi is the position of particle I. I have some inertia, I have some friction. This is a... Okay. This is supposed to be a Greek z. Okay, I cannot make it very well, but I use this for friction because xi, okay, I don't know, it's a choice of... So there will be the potential, and then there will be some noise, xi. Okay, so the total potential V is just the sum of pair potentials. And so here I have, I mean, if I, and the noise is a Langevin, I mean, is a white noise with 0 average. And delta correlation in time. So this is the standard Langevin equation. I hope you have seen this once, at least. Anyway, if you're not familiar with the Langevin equation, you can just think that this friction coefficient is 0. So if you drop, if this This is a Gaussian variable, so it has mean 0 and this variance. If you put z equal to 0, the variance is 0, so the variable is 0. So you remove this and you remove this, and you just have Newton dynamics. So this is just a generalization of Newton dynamics, where you suppose that your particles are Brownian particles immersed in some solvent, and the solvent is providing a friction and a noise, and the noise comes from the collisions of the particles with your solvent. Okay. So one can simplify the problem by considering what is called the overdamped limit of the Langevin equation, where you set the mass equal to 0, and you essentially everything is dominated by friction. But it's not needed. But I can do it for just to lighten the notation. Okay. Now this is the problem. Maybe okay. Let's write here the. So, sorry, this is, this is in the dimensions. So the I is the index of the particle, and mu is the index of the spatial coordinate. So these are vectors, all these are vectors. And so the coordinates of this noise are delta correlated in space. Okay, so this is the problem I would like to solve. So solving the problem means I want to be able, for example, to compute correlations. For example, I would like to compute the mean-square displacement of this group, of these particles. And okay, this is in equilibrium. So at t equals 0, I start with the Gibbs distribution, and this equation is known to keep the equilibrium. So because, okay, here there is temperature. Sorry, I forgot the friction. So you can show that if you start in equilibrium at temperature beta, and if the noise has the same temperature T equal to 1 over beta, then the system is going to stay in equilibrium at all times. Okay? So at any positive time, this is the correct distribution, but you would like to compute time-dependent properties. And now, before I start doing that, I just need to make a little generalization that is going to be important, which is this is a white noise, but it can be generalized to a colored noise. So I can introduce a kernel K, and I can say, okay, the friction is going to be instead of being just proportional to x of t, as some kind of delay, okay? So the friction at time t is an integral over the previous times of some kernel times the velocity at previous time. So that's the generalization, and the rest is the same. And I put the noise here. And if I do this, and I want to have an equilibrium dynamics, then the noise should be should have the same kernel. So it should be T K of T minus T prime. The variance of the noise should be given by the same kernel. So if I have the same kernel here and here, then this equation will preserve the equilibrium, which is related to the fluctuation-dissipation relation. I hope. So I don't know if, okay. If you have questions on this, maybe we can, I don't know, organize a tutorial or something, but I don't have time now to discuss the details of this, but this is the starting point. So, okay, and our goal is to compute for example, the mean-square displacement. So the mean-square displacement is going to be 1 over n times the average of sum over I of xi of t minus xi of 0 square average. Okay? I mean, in principle, it can be any pair of times. But if you are in equilibrium, everything is time translational invariant, right? Because if the equilibrium if this distribution is correct at any time, I can start at t equals 0, but I can also run the dynamics for some time, and then I set a new starting time, and everything will be the same because I will always start from the same distribution. So everything is time translational invariant, and all the correlation functions are functions of the differences of times. Okay. Now, what I'm going to do, so I want to use the same idea. Okay, so this derivation with this kind of, I say the end-waving argument, but they are also very clear, I think, from the physical point of view, is due to Gregor Szamel. So there is a PRL, I think last year, where he derived the result in this way. Before, Jorge, myself, and Thibaut Membourg had derived the same result using path integrals, and it was a long calculation. This is much simpler. Now, so the idea is really to use the same, okay, let me write things in this way. What I want to do, I will isolate one particle I, and I write the equation for this particle in this form. So I drop the mass, I set the mass to 0, so it's overdamped. But I mean, if you want, you can think that here is there is the mx dot, x double dot. I mean, you can imagine that it's always to change anything. So I have my Langevin equation, and I have, so the friction is going to be equal to the force, and to the Brownian force, and then there is this Fi, which is the total force that comes from the other particles. And Fi of t is the derivative of the total potential, so it's written as a sum over all the other particles j, different from I, of the gradient of the potential, which is a function of xi minus xj. And so I can also write it as a sum over j of some fj to I of t, where this means that this is the force that particle j is exerting on particle I. Okay. Now I'm going to use the property that I already used for the thermodynamics, the two properties. So one is that there are many particles around each given particle, because in infinite dimension, as I told you, there is space for exponentially many particles in D around any particle. So I have a particle here, this is xi, and I have the neighbors. So I'm going to use that there are many neighbors, and also I'm going to use that they are essentially uncorrelated, which is the same assumption I made in the thermodynamics to drop all the virial coefficients except the first one. Okay, I use the fact that, as I answered to the question, that was very useful, so thanks again. I will use the fact that two particles that are neighbors of the same particle are not interacting directly, so they are essentially uncorrelated. So under these two assumptions, what happens? Essentially what happens is that you see that now the force, so the particle I is feeling a force, which is the sum of all these forces. And because there are many terms and they are uncorrelated, this is a sum of many random variables, so it's going to become a Gaussian. So this is the central limit theorem. Central limit theorem. This is going to become a Gaussian variable. Okay? So a Gaussian variable is only characterized by its mean and its variance. So I need to compute the mean and the variance of this variable. Okay, so what is the mean? So I will start, what is the mean? So I will start by assuming that the particle is not moving, okay? The particle I. So if the particle I is not moving, then I have essentially I have an obstacle in a fluid. So all the other particles are moving, and by isotropy of the fluid, the force is 0, the average of the force. Okay. And the variance, I can write the variance as, I will call it M of t minus t prime. This is going to be the variance of Fi mu of t, Fi mu of t prime. So again, because of the isotropy, the different components with different spatial index will be uncorrelated. So I only take the same mu here. And this is going to be sum over j and k that are both different from I of f j to I mu of t, f k to I mu of t prime. Right? I just took this sum, so I put the sum here, and I get a double sum. But now I can use that these particles are, so this will be particle j, this will be particle k, and they are uncorrelated. So I can drop all the terms with j different from k, because if j is different from k, these are uncorrelated, so this product, the average of the product becomes the product of the averages, but the average is 0. So this is going to be the sum over j of f j to I mu of t, f j to I mu of t prime. Okay. And the last thing I can do, I can realize that, okay, I is not special. All the particles are identical. So I can also average over I. So I can add 1 over n sum over I. Yes. Which one? Yes. I agree. But if the particle I is not moving and all the other particles are moving, each of them eventually is going to be everywhere. So on average, this is an average over all possible realization of the dynamics. So the particle J can be everywhere because it's a liquid. But okay, I agree, it's a bit, this is actually a very tricky point, but as I told you, this is not going to be a fully satisfactory derivation. You just have to try to follow the idea. I will get to a result, and I will tell you that then the result can be obtained in a rigorous way. But no, they're different, yes. Sorry, what? X, yes, this is X. Just that the particle I, for the moment, I'm assuming that the particle I is not moving. I'm looking to a particle that is just there, and the fluid is around it, and I'm looking to the statistics of the force. The other particles are moving regularly. And, okay, this is just, okay. So this is the sum over J different from I, but then I is not special, so I can average over I, so this is going to be the same thing, but I can sum over I and J. Okay, so this is when it's not moving, and okay, I don't know this function M, but it exists, this function exists. And now what happens if the particle is moving? No, because okay, first of all, I would like to write everything in the frame of the lab. And second, okay, the frame of the particle is moving, and it's changing velocity. It's not really an inertial thing, no, so it could be tricky. So I prefer to stay in the frame of the lab. So what's going to happen if x dot is non-zero? Okay, now you will not be happy, but I mean, you have to trust me because, as I said, this is just to give you the ideas. I mean, it can be done a bit more probably, but essentially what I'm going to say is that, okay, imagine that you have a Brownian particle. So you have a very big particle, and it's surrounded by many small particles. So it will feel the kicks coming from the other particle, and this is essentially this part. And now if I move the particle, the big particle in the fluid with some velocity, it will feel a friction, right? So I'm going to say that the effect of moving is only going to shift the average. So the average of the force in presence of a velocity will be a friction. So it will be minus, in general it will be minus, it will be proportional to the velocity. Okay, so this is, okay. It will be proportional to the velocity with some kernel, k. And actually, if the fluid around the particle is in equilibrium, which is the hypothesis that I made at the beginning, then this kernel must be the same of the autocorrelation of the force. And this is imposed by the fluctuation dissipation relation. So this is going to be minus beta m times x dot. It's possible to derive this by doing a fluctuation dissipation treatment. We have a paper on arXiv. If you want more details, there is a paper by Agoritsas, Membur, and me on arXiv this summer, where this is done a bit more carefully by, instead of assuming that everything is in equilibrium, you can say, okay, the fluid is not in equilibrium, but I can do some essentially fluctuation dissipation reasoning, and I get to the same result. So what I'm going to claim is that, to assume if you want, is that when x dot is non-zero, then the force has a component which is the average, which is written in this way, it's just a friction, and some fluctuations that are controlled by these variance. So essentially, I'm deriving the Brownian motion. And you know, when you derive the Brownian motion, you use the fact that your particle is very big. So the neighbors, the small particles of the solvent that collide with it are essentially uncorrelated, and there are many. So I used exactly the same two assumptions, except that that my central particle has the same size of the others, but it's in infinite dimension. So in infinite dimension, there is a lot of space around it, and so there is space to put many particles and to have them uncorrelated. Sorry? No, sorry, this is, if you want, is the average over, this is the average over the other particles at fixed. Okay, sorry. So what I'm trying to do, if you want, is so this is an equation for xi that is not closed. It depends on all the other particles. What I'm trying to do is that I'm trying to isolate one particle and try to write a kind of self-consistent equation for the trajectory of just one particle that is supposed to be in some kind of effective medium, that is the rest of the fluid. So I want to have xi of t fixed, and I want to compute the statistics of the force over all the other particles, given the trajectory of xi. Fine? So if you accept this, then I can erase all this, and I can say, okay, then this force is going to be decomposed into an average force, which is this. So, okay, I will call it F average, where, okay, this average is on the other particles at fixed I. So, I don't know, if you want, I can write it in this way. It's an average over all the j different from I. So then I have this average plus some fluctuating part, plus the white noise. Yes? Yes. No. Sorry, this means that I sum over j and k, and not on I, but j and k have to be different from I. Which one? This one and this one. Here I'm summing on I and j, but they are different. Yes, sorry, I put a parenthesis to mean that I don't sum over that. But then I say, okay, up to here I is fixed. But then I say, okay, for the computation of m, I can average over I because they're all equal. In the end, I focus on one particle, but in the fluid they're all identical. So okay. Okay, so you see now I have this equation, and so I can write it in another way. I can say, okay, I have my friction term. I will bring this average on the other side, so I get plus beta times the integral between 0 and t of m of t minus t prime x dot I of t prime equal to, and now I have these two terms. So this is a white noise, and this is also a Gaussian noise, but it's not white, it's colored, because it has zero average, but it has some correlation. So I will group them together, and I will call, yes, so I will call this capital Xi of t, and capital Xi of t is the sum of these two. I will assume that the white force is uncorrelated from this. I mean, this is correct because at equal times they are. Okay, sorry. Okay, this is not completely. I mean, anyway, I will assume that they are uncorrelated because this is on I and this comes from the other particles. And then I have that. So the average of this noise is going to be 0, and its variance, because they are uncorrelated, is going to be the sum of the two. It will be the sum of the variance of Xi, which is a delta. Let's put, okay. It's going to be uncorrelated over particles and uncorrelated over spatial directions, and then I have 2t times delta of t minus t prime plus m. Okay. Is it fine up to here? So now I got, okay, so now this is a kind of closed equation for the particle I. Do you agree? Because I mean, now you see it's, okay, this is essentially Brownian motion because it's only something like x dot. There is some kernel acting on x dot plus noise. So it's like this one, but with no potential. It's a particle diffusing. It's diffusing with a kernel m, which is the same in the friction and in the random force because I'm in equilibrium. So now, and it's closed, but I have to now to find an equation for m. So how do I find the equation for m? So I told you that m, let's write it here, m is the average of the force between particle j and particle I. So I have to close this equation. So let me I have 10 minutes, so let's try to do this last step so that tomorrow we can restart from the final equations. Perhaps I will, if I write here, it's better, right? Okay. So now I have two particles, and I want to know the autocorrelation of the force between these two particles. So let's say, okay, this is J, this is I, and these are the other particles, and there will be other particles. surrounding J. Okay, so there is J, there is I, and there are all the other particles. And this is the force that J exerts on I. What I'm going to assume is that the particles that are neighbors of J are not neighbors of I. Always, because in infinite dimension, you should think, okay, I have these two particles. This is one of the neighbors of J, but then there is a lot of space. So the probability that one of the particles that are neighbors of J is also a neighbor of I is very small. So I can think that I have two disjoint sets. One is the neighbors of J, and one is the neighbors of I. And so I'm going to write this equation in this way. I will write that the equation, let me use the notations that I have here. I write this in this way. The total force on I is going to be a contribution that comes from all the neighbors except J, which I write in this way. It's Fi with subscript J plus the force of J plus the noise. And then I have the same for J. This is going to be Fj, where I remove I, plus the force of which is minus the force. So this will be minus the force of J on I, plus the noise of J. Now the point is, if I consider the motion of I and of J, the motion of I and J can happen in d directions, and the force between I and J is defines one particular direction, which is the direction that connects I and J. But most of the times, because I have d directions, I have many orthogonal directions here where I can move, most of the time the motion is going to be orthogonal. So if you want this, you can think that this term is a small perturbation of of the total force, because it's going most of the time is going to be orthogonal to the motion. And also, here you have d terms, d minus 1. If you have order d neighbors, okay, you have order d neighbors that contribute, and so this is one out of d terms. So in general, I could drop this term, and if I drop this term, then I am in the same situation as before. So I have two particles that are completely disconnected. Each of them has a neighbor that provides a bath. So I end up with this equation. Okay. So then, if it's fine for you, then I will write this in this way. I will have an equation for I, which is the same as the one I derived before. So it's going to be this is going to be equal to the noise. This is an I. And then I have this correction that comes from this additional term, which in general, which I can neglect. Okay, I should neglect it if I'm only interested in the motion of I. And I have the same for J. Because all my argument was based on the idea that there was an infinite number of neighbors. So if I isolate one of the neighbors, it doesn't change anything to the argument, except if I want to know the motion parallel to the distance between two given neighbors, which is what I'm interested in now. So I have these two equations. So equation for I and equation for J, where I introduce now this thermal bath M that comes from all the neighbors, all the other neighbors. And this function M is the same as before, because, okay, here there are d minus 1 neighbors, but it doesn't change anything when d is infinite. And I have this term. So if I'm interested in I and J, I drop the term. But now I'm interested in the relative motion of I and J. So if I consider the relative motion of I and J, then this is parallel to this force. So the contributions will be coherent, and I cannot drop it. Okay, to be convinced of this, you should think a bit about it, and I will try maybe to give a better argument, but okay, for the moment, let's try. So I take the difference. So now I want to focus on the relative distance, which is xi minus xj. And so I can write an equation. I can take the difference of these two equations, and I will also divide by 2 for later convenience. So I get r dot here. When I take the difference, I get z times r dot. Let's drop the ij because now I don't need it anymore. Plus beta integral of r dot beta over 2. And then I get equal, this is going to be equal to psi of t. So psi is going to be the difference of the two noises divided by 2. And then I have plus the force. Now this force is a function of the distance between I and j. So I can write it as f of r of t. So I mean, from this point of view, in the equation for r, this is a contribution of order 1, because now it's really okay. So so now I got an equation for the relative motion of two particles, which is this one, and the noises. So this is my equation for the relative motion of r, and the noises the two noises there are uncorrelated. So the statistics of this new noise psi is what is just okay. It has 0 average, and it has a variance which is just 1/2 of the variance of one of these two. So it's going to be z delta plus 1/2 m. Anyway. And now we can close everything, because now the m, so m is the autocorrelation of the force between j and I, between times t and t prime, and this was the average over all the particles j for a given I, but I can think now that this is an average over this effective process that I got here. So I can write just that m of t minus t prime is equal to some, okay, first of all, I can put t equals 0 here, right? Because I mean, it's time translational invariant. So I can correlate between t and 0. Now, okay, now let's do it in 2 steps. When both times are equal to 0, so if I put 0 and 0, what is this? So this is 1 over n, sum over I different from j of the square of f at time 0. And this is just a thermodynamic average. And you can write it by introducing the g of r. So this is going to be rho over d times the integral over r. I call it r0 because it's the initial of g of r0 times f of r0 square. Okay, here f of r is minus gradient of v of r. Okay. Is it fine? I mean, if you put 0 and 0, this is just, now it's a thermodynamic average. And you know that if you have a thermodynamic average of some function that depends on I and j, summed over I different from j, this can be written, by definition of g of r, can be written in this way. I hope you see it. Otherwise, I can discuss it tomorrow because now I'm out of time. So, this is at time equal to 0, and now if I put time here back, I mean, it's going to be the same, except I should put the time here. So I will have to extract the initial distance from G, and then I have to put f of r of t, average, over the dynamics, times f of R0. So I'm done. Let me just comment the result, and then tomorrow we restart from here. So what I did, I mean, I started from the Langevin equation for all the particles. Then I said, okay, if I isolate one particle and treat the rest as a bat, then I get this equation that is the same for all the particles. I put an I, but of course I can drop the I now because they're all identical. And this equation depends only on this kernel M. The kernel M is unknown and for the moment, and it's an average of the force between two particles. Now, I can take now a process with two particles, and if I assume that the other neighbors provide a thermal bath that is independent for each of the two particles, then I have the same equation. But if I want to look to the relative motion, then I should isolate this term, which is the force, which is going to be parallel to the relative motion, so it's important. So I get the same equation, but with this term added to it, and the noise, which is the difference of the noises, so it has the same statistics. And then I can express the kernel as an average over this process. So now I got a closed... Exactly. So now if I want to... is the average over that one. So if I want to solve these equations and get M, I should do the following thing. I choose an R0, as I want. Then I run this process starting from R of t equal to R of 0 at time 0. I run this process many times with different nodes and with some M. So I start with some M, if you want. I start with a guess for M. I do it self-consistent. I start with a guess for M. I take an R0. I solve this dynamics for given R0 many times, and I compute the average of f of r at time t. And then I integrate over R0 with g of R0. And by the way, g of R0, which I forgot, is just, because we are in infinite dimensions, it's just e to the minus beta v. So this is closed. I get a new M, and then I redo it many times until convergence. So I get M, and once I get M, I can study the motion of the particles, and from this, tomorrow I will derive the equation for the mean square displacement. So you can compute all the correlations that you want from this. Okay, so I think I can stop here, and tomorrow I will analyze these equations and see how they predict a glass transition. This one? No. I don't think it's going in the...
So I have two questions. First of all, when you write that expression of G of R, that is what I actually understand, this V of R, or is it the effective V of R? So it's an effective interaction, I guess. So basically, this is not exactly V of R. In a sense, when you have many bodies, many particles are there, and this pair potential is considered when you actually consider the, you actually neglect the many body contributions, right?
So I'm not. So if you want, when you derive the virial, I mean the G of R is pure thermodynamics. It doesn't depend on the dynamics. So you have to derive it from the virial series. When you do the virial series, you see that G of R, essentially, I mean, G of R is the probability of finding a particle at distance r, given that there is a particle in the origin. Okay? essentially. I mean, with some.
So I'm not still clear about what does it means that pair potential is equal to the effective potential or effective interaction.
It's if you want, it's a kind of low density.
It's only valid in the low density.
Yes, but in infinite dimension, it's always a kind of low density. I mean, you can always. It's the same argument that I used to truncate the virial expansion at the second order. If you want, you are it's strong interaction, but it's low density. Because you should think that you have a space, you have a particle. Around the particle, there are, in principle, you can put exponentially many particles, e to the d particles, but you only put order d. And so if you want, your liquid is dense, I mean, it's strongly interacting, but it's there are many holes, if you want. I don't know. I don't have intuition on large dimensions, so I can only wave my hands. But I mean, if you look to the mathematics of it, the G of R is e to the minus beta v plus corrections, and the corrections are exponentially small in d. So you can drop them. But still, the result is not an ideal gas. I mean, this will have a glass transition. I will show you tomorrow that this has a glass transition. So it will be slow and dense and stuck. But you only need the first virial to do that in infinite dimensions.
And one more question. So just give us some insight about how does this P of xt behaves with time in these cases. In this case, when you have this...
P of xt?
Yes. So, for example, what happens if you have the normal Langevin equation, this Pxt is a Gaussian, right? So that decays with time. So in this case, you have some...
I don't understand. What are you talking? What is...
No. So basically what I am asking is the analogous Fokker-Planck description of this thing. How does this P of xt behaves with time?
So this... You mean in infinite dimensions? In a Fokker-Planck way. So, okay, this is a Langevin for many body systems. So you have n particles. So you will have a Fokker-Planck with n terms. So Fokker-Planck will be something like a sum over I of d over dxi square plus. I mean, there will be a sum over all the particles, and you have a many body distribution, which will be the solution of the Fokker-Planck. And I mean, I'm starting in equilibrium, so the Fokker-Planck will tell you that you stay in equilibrium at all times. So this is for the many-body problem. And then if you want, I'm trying to map the many-body Fokker-Planck equation into a one-body effective Fokker-Planck equation, Langevin process. But for this, I needed to introduce a colored noise. So the
reason I'm asking is because when you attempt to write the Fokker-Planck description or some dynamic equation of this P of xt, it will end up with something non-Gaussian.
Okay, I see. So, okay, this is tricky. So this is the Langevin equation for one particle, and this is Gaussian because it's linear. You see that x is a Brownian motion given m. So it's a Brownian motion with colored noise. So if this noise is Gaussian, then x is going to be Gaussian at all times. And we are going to see that it will diffuse at low density and it will be stuck at high density, but it will still be Gaussian. However, the equation for R is nonlinear because there is F. So this is not Gaussian. So if you want, each particle individually is performing a Brownian motion in a colored noise, but the distance between two particles that are neighbors, let's say, is not Gaussian, and then it will give you this self-consistent equation for the kernel of the noise.
So one more question now. So this okay, maybe. So we'll discuss later.